Good afternoon, all. Uh, in this lecture, we will discuss about application of GNSS for the atmospheric studies. And we already know that. So basically, the primary objective of GNSS, or very commonly, the basically the GPS and in the GNSS, basically, it is a common word. So Global Navigation Satellite System. Inside that, various constellations comes. GPS, like India, we have a IIRS. We have a Galileo from the European Union, and we have a GLONASS from the Russia. So various constellations are there. Common name is basically we are calling as a GNSS. So we already know that the primary objective of these constellations to provide the basically precise positioning, or these are basically used primarily for the precise positioning. However, the signals, whatever coming from the satellite to the receiver on ground or in space, can be used for the to derive the various other parameters. So one side, for the precise positioning, we are doing the corrections. Like when the signal will come from the satellite to the receiver, so it will pass through the atmosphere and maybe the ionosphere, the troposphere, and then we need to do the corrections because of these, because ionosphere electrons contents are there, then water vapor, the other molecule particles are there. They are in the atmosphere, troposphere. So because of that, some delay will be there in the signal. So we are removing basically these delays for the precise positioning. But on the other side, if we see these signals, we can utilize this delay to determine the basically the tropospheric properties or the ionospheric properties. So on these, when we are ionospheric or tropospheric parameters, basically, so these parameters further can be used for in the weather forecasting or numerical weather predictions and different weather analysis. So we will discuss more in more detail, and first we will discuss the some error parts, and then finally second parts we will discuss the atmospheric parameter retrieval. So these are basically, since we use for the navigation purpose, primary positioning and the navigation. So navigations are basically is a science of charting one's own route from A point to the B point with respect to known references, both in spatial as well as in temporal domain. Nowadays, we are you very well know about navigation concept. Anyone wants to put onto the somewhere in the building nearby areas, or someone wants to search to the points B, just want to go, just put the value that name in the Google map, and you are just taken towards the that point. Okay, so it's very useful for the navigation and similarly to finding the position. So it is a science to determine one's own location in known reference frame with some inaccuracy. So maybe some inaccuracy, or we can say in another word, try to do more precise, getting this position more precise way. So it's basically to find out the own position. Where is the whether our own positions, so some objects locations, we can usually find out. So we then very commonly this we use this global positioning system, and it is a very well known. It is an all-weather space-based navigation system developed by the basically this U.S. Department of Defense to satisfy the requirements for the military forces to accurately determine their position, velocity, and time in a common reference system anywhere on or near the Earth on a continuous basis. So basically, it was defined, derived basically for the primarily for the U.S. forces but later it was maybe applicable, or it was maybe made available to all the users. So 1973, the US DoD, the Department of Defense, decided to establish, develop, test, acquire, and deploy a spaceborne global positioning system, and which is basically known as the Navistar GPS. That's a navigation, satellite timing, and ranging global positioning system. Some basics about the global positioning system is that GPS is basically worldwide radio navigation system. We already know that it covers the whole globe, and there are the 24 satellite in this constellation. There are some 8 redundant satellite as well, but at a time you may get that 24 satellites are in operation. Then these are divided into 6 orbital plane. So each plane will be having 4 satellites. Then it is having a 55-degree inclination, and orbital period is around 12 hours, and altitude is around 20,200 kilometer approximately, and orbit is around orbital period is basically 12 hourly orbit it is there. I will show you the picture as well in the coming slides. So GPS is having basically 3 segments. One is a space segment. There basically these 24 satellites are orbiting around the Earth. Then there is a there is a control segment. Once these are orbiting around the Earth, so throughout the globe, if you can see in the picture on the top right bottom, there are the monitoring stations are there. So monitoring, it will continuously monitor, and this will send the data to the master control center here. What will be happening there? Master control center station will basically the data will be coming from all over the globe. That's a monitoring from the monitoring station. It will analyze the data, and it will do the precise orbit determination of the satellite. That means where is the basically exact location of the satellite in the orbit. This will basically analyze in the master control station. Then finally, this will be through ground antennas. The uplink will be there. One uplinking will be there to the GPS satellite. So you know that's a GPS satellite are basically sending its own positions to the receiver, which is generally updating at 2 hours at the interval of 2 hours. So they are basically, it is maybe what we can say, that's basically an orbit analyzed by, or orbit determination carried out by the master control station. Okay. So then finally, this information will transmitted to the user segment. User is having a receiver which is continuously receiving these signals from the GPS satellites. So this will be utilized for the various application, whether it's a transportation or navigation purpose, or finding the its own position. So there are these master control facility, and where are these stations are located are shown in the right side on the world map. Then when we are estimating position using the GPS satellites, so there are basically various sources, various error sources in the GPS data. Like in the space segment, when we talk about space segment, then there is a satellite clock error and there is a ephemeris error. So satellite clock, onboard atomic clocks are there, though they are very much precise, but still some error can exist there itself. Then we have an ephemeris error. Ephemeris error in the sense, as I just now told, that's a master control facility. That's they are sending basically the latestly precise determined orbit to the satellite. Okay, so there may be some storage limitation, or maybe some because of any other reason errors will be there. So it may be it may cause an ephemeris error as well. So in that error, and then satellite clock error. These are in the space segment side. Then once comes on to the signal will travel from the satellite to the receiver. So it will pass through the ionosphere and the troposphere. So definitely in the ionosphere, there, because of total electron contents are there, because of electron contents, this delay will be arises here. And then the troposphere, maybe gas molecules are there, and water vapor it is there. So because of that, error will be there. So, and it will experience a delay. Basically, satellite signal will experience one delay. Okay, but so it's supposed to follow the straight path or the straight line path, but actually because of this ionosphere and troposphere, it will be deviated from the its geometric path, and the delay will be there to reach the signal. Okay, and then we have a finally, that's a third type of errors are there, local error. Local error in the sense like a receiver error. So receiver, we are having there also some clock error, or the receiver side error can be there. It may not be able to that much precise measurement, able to do the precise measurements. And then we have another error, that's basically multipath error. So multipath in the sense the signals are basically reflected from the surface or the buildings, and then it is reaching to the receiver. So instead of it's supposed to reach directly from satellite to the receiver, but instead of that, it is following the other path, like it is reflected from the buildings or roads or surfaces, what we can say, different surfaces. Okay, so these type of errors are there. So these has to be removed for the basically precise positioning. So now we are, I'm just talking about the more in the basically ionosphere and the troposphere side. So ionosphere delay is basically proportional to the frequency of radio waves. So whatever the frequency is there, like L1 and L2, in case of GPS signal, it is proportional to radio waves. So delay can be calculated by measuring the differences in the travel time from two frequencies. So obviously, the travel time will be different for the though two different frequencies. So the delay can be measured, and measuring the differences in the travel time. So delay can be estimated using that. And the refraction or the GPS signal as it passes through the atmosphere can alternately be viewed as an increase in the path length. It is called the path delay. So you can see here the receiver, the extra the red, the mark is there here. This is basically excess path length. So satellite to the signal, it's supposed to follow this path, but because of this troposphere and the ionosphere error, this path length is extra. Path length is extra in the sense we can discuss like this. Suppose at time t from the satellite signal is starting, and t1 time it is reaching at the receiver. So it's up. So the total path, it will be like a t minus t1 multiplied by the velocity of light c. So total path will be there. But thing is that because of ionosphere and the troposphere, one delay is observed. So because of that delay, suppose delta t, that difference, time delay it is there, then delta t multiplied by the c is the basically the delay path length. Because of that, excess length will be there. So the troposphere slow, because of in the troposphere, GPS frequencies equally. This means the tropospheric delay must be modeled as a free parameter in the GPS processing. So if you can see here, total atmospheric delay is because of the ionospheric delay and the tropospheric delay. Ionospheric delay is maybe the total electron contents are there because of that, and from that tropospheric delay is because of the hydrostatic delay and the wet delay, both are there. Okay, so we will derive these parameters PWB. So atmospheric error sources we were discussing. So ionosphere, it is basically around 14 hours. It will be a local time. It will be the delay will be maximum, and it is around 5 to 15 millimeter at the zenith side. Okay, over the zenith. And in extreme cases, it will be varying from 0.15 to 50 meter at the zenith. Higher frequency have a less effect because it's a proportional to 1 upon f square. So frequency is square. So frequency will be high, then delay will be less. Error correction by the basically we are doing here using the dual frequency methods. Then on other side, the troposphere, if we see, there are the two type of delays, dry delay and the wet delay. Dry delay is basically 90% of the almost part of the tropospheric delay is the dry delay, almost 90%. And it needs atmospheric pressure and the temperatures. Accurate pressure is critical. We need to have to precise hydrostatic to determine the precise hydrostatic delay. We need to have a precise pressure as well. And on the zenith side, if we see over the zenith, it is around 2.2 meter. It will be there. So this much delay is because of the dry delay or hydrostatic delay. Then wet delay, it is basically 10% of the total effect. And it is a model accuracy, whatever are available, it needs 10 to 15%, and it need humidity along path. So then only we can find out how much wet delay will be there. And it is around 20 centimeter at the zenith. Okay, so these are the basically hydrostatic and the wet delays. So it divided into basically, as we told, that's wet delay and dry delay or hydrostatic delay. Wet delay is because of the water vapor content in the atmosphere, and dry delay is basically gas molecules in the atmosphere, and it contains the almost 90% part. For the basically these delays, we are having a modeling we are doing using various models are available. Neal model, Hopmeal model, Sastamoen model. So using these models, we can derive the tropospheric delays. Okay, and these residual tropospheric delay also estimated using the Kalman-Feld. Then we are also having a the delay due to the atmosphere is a basically major part here. So okay, now other type of errors are there in the which are called the local errors. So multipath errors depends upon the geographical location of the site. So it depends, like if your receiver is near to the building, then definitely multipath errors will be more. But if your receiver is located in such a place where no building or no surrounding outside any objects are there, then it is having a directly it will be having a signals. So it depends where the the receiver is located. Second thing, azimuth and the elevation of the satellite. So maybe the lower elevations when you are coming, it may be reflecting at certain surfaces, but if you see the overhead when it is on zenith side, or maybe near to the 90 degree or 80 to 90 degree, there is no obstruction. Directly send signal will come from satellite to the satellite to the receiver. So it depends on the azimuth and the elevation as well. Similarly, azimuth means the directions with angular directions. So maybe in particular direction, it may be some trees or some buildings can be there. On the other side, it may be clear. So the multipath error will depend on the azimuth and the elevation as well. Then site selection. Reference site should have a clear sky with no obstruction, and clearly for means to avoid these errors, an antenna should be placed at a particular height. Okay, it should not be like in particular you are fixing near to the ground. So some particular height should be there with reference to the local scenario. And there is an antenna design as well. There is a concept of to avoid this errors. Now we also have receiver noise. So in GPS receiver, because it is like electronic device, so in GPS receiver, the noise translates into error in range measurements. So RF radio frequency radiation sensed by antenna within the band of interest but unrelated to the signal. Noise introduced by the antenna, amplifiers, cables, and the receivers. So these are the basically sources, local sources. Because of that, some error can be there. So this will introduce an errors in the range measurements. So these are the basically different type of errors. We need to consider these errors before the precise point positioning. Apart from that, the space segment side errors are also there. So satellite when is moving, so it may be basically towards the, if you see satellite position at time t, it may be deviate, it may be showing certain different orbit, maybe in the change in the XYZ direction, because you know the satellite position will be supposed measured in the XYZ direction. So if suppose there is a difference in the X direction, it will be delta X, Y it will be delta Y, Z will be delta Z. So because of that, satellite will show maybe the somewhere else position in that maybe a little different or deviated orbit. And because of that, ephemeris, whatever it is, maybe having a little errors, or maybe the errors, it may be a cross track, a long track, and in the radial directions. Okay, so it may be a little change in the basically XYZ orbit. Okay, and one thing is this one. Second thing, satellite is only broadcasting the at suppose 2 hours or 0 hours, 0 hours, 0 minutes, 0 seconds. Like one ephemeris set this is giving, like it's telling my position is X, Y, Z at the point at the time 0, 0, 0, 0 hour, 0 minute, 0 second. Now what you will do, using this you will try to propagate the orbit. Okay, you will try to propagate the orbit because your measurement suppose at the time of 0 hours 0 minutes at 1 second. So you need to propagate this orbit. So in the propagation itself, the model whatever you are using, depending on that, some errors can be there. It may not be that much precise. So where it should be exactly, it may be from the predictions, it may not be at that particular position. So some difference can be there. So in the prediction also some error can arise from this ephemeris. So we need to take care all these parameter while we are estimating the position. Now on the other side, if we see, excuse me, on the other side, if we see, that's basically these are the basically errors. We need to, like troposphere and ionosphere, for the we need to remove or taking care at the time of positioning. On the other side, if we see, these signals are also applicable or used basically for the determining the different parameters. So in traditional GNSS application, signals arriving at a receiver antenna from nearby reflecting surfaces interfere with the signals received directly from the satellite, which can often result in a reduction of the position accuracy. By property of processing the scattered signal, this system can be configured either as an altimeter or an scatterometer, allowing us to estimate characteristics of land or ocean surface, such as height, roughness, or dielectric properties of the underlying media. So by properly processing the scattered signals, so whatever the reflected signals are coming from the ground, we can utilize these signals and for estimation of the characteristic of the different surfaces, like ocean, height, roughness, ocean surface such as height, roughness, and dielectric properties. Using various methods, the atmospheric and the geophysical parameter can be estimated, like water vapor, total electron content, mesoscale oceanotopography, ocean water surface winds, soil moisture, vegetation, snowpack, all these things, water surface elevation, and sea ice. Depending on the platform of the GNSS receiver, it may be stationary, static receiver, it may be on the airborne, or it may be on the satellite, spaceborne. The capability of this technique and a specific method for processing of reflected signal may vary. So where we are going to put, and based on that, the processing techniques may vary. So we talk about in this related to the like on the ionosphere and the troposphere in the context of space and the ground-based GNSS receivers. So there may be two types of receivers. One we are putting into the space. Space in the sense we are fixing a receiver onto a like satellite. Okay. And that satellite will receive the signals continuously, and both satellites are receiving. Now the thing is that when we are putting a satellite on the receiver on the satellite, so satellite should be below to the GPS satellite. It cannot go up, because GPS satellite is around 20,000, altitude is around 20,200 kilometers. On the other side, the low Earth orbit satellite are of altitude 800 kilometers around. So we will fix these receivers onto that particular the low Earth orbit satellite, and then it will wherever it will revolve or orbit around the Earth, it will continuously receive the signals from the GPS satellites. So this is a space-borne. Now another is a ground-based GNSS receiver. So ground-based, what we are doing, we are having a receiver. We are for the analysis at a particular point or particular locations analysis, we will fix this GNSS receiver and at the ground. So space-borne receiver is basically continuously moving. Continuously moving means like orbit is around 90 minutes it is taking to complete the orbit, the low Earth orbit satellite. So when we put the receiver onto that such type of satellite, it will also rotate, and it will globally it will be moving, because satellite is rotating around the Earth or orbiting around the Earth. Okay, so it's the global pictures will come, global coverage will be there. But it's ground based. When we are talking about, we are fixing even the receiver at ground, and there only the particular local information only can be collected. Okay, so now there is a from the space and the ground. Now there another two types are there where the signals can these two types of analysis possible using this GNSS signals. Now one is the receiver, which are directly also receiving the satellite signals from the GPS satellite. Now again some of the signals will be reflected from the surface, and this also can be received by a receiver. So when we talk about the direct signals, from that atmospheric or ionospheric studies can be done. We can estimate the TEC, we can estimate the water vapor content. And when we talk about a reflected signal surfaces, when the signal is reflected from the nearby surfaces, then it is called a reflectometry for the Earth studies. Basically, Earth surface studies, and the parameters soil moisture, snow depth, water level, and the ocean wind remote it may be useful. And the parameters soil moisture, snow depth, water level can be derived. Okay, so it is also used for the ocean wind remote sensing. So these are the basically two type of signals generally used for the different applications. Application of the basically GNSS signals. So we talk about here now different type of platform, and then we will go for the application side. So remote sensing of the troposphere and the stratosphere by gauging the refraction or slowing and the bending of GPS signal that propagate through the atmosphere. We can derive the property of pressure, temperature, and the humidity. Depending on the location of the GPS receiver, two approaches for the GPS meteorology. Okay, so one is a ground-based GPS meteorology and the space-based. So in the ground-based, if you see left side, one antenna it is there, which is fixed. You can see the nearby solar panel it is there, and for the power purpose, and we may fix at interior as well, wherever we want to study at a particular location, we can fix it this receiver, and it is covered, so it will not be maybe disturbed by any wild animals or like this, and continuous maybe no person required actually continuous basis to monitor it, and this solar panel is there for the power purpose. So if you see this such receiver which will directly receiving the signals from the GPS satellite. So this is a ground based when we are putting this. So retrieval basically used for the retrieval of the precipitable water vapor, and it's a time series of PWV for the local observing GPS ground station, horizontal distribution possible with a dense network of GPS stations. So continuous monitoring is there since, so we can obtain the time series data. It's continuously, maybe 1 second interval, it may be a 30-second interval. So it will give you one measurement at an interval of 1 second or the 30-second interval. Okay, and it's a horizontal distribution possible with a dense network of the GPS station. Means when we are doing for the weather prediction analysis or NWP, so in this case we should have some more number of receiver in the ground, on the ground, so which are having a certain distance, like maybe in the 50 to 60 kilometer or 70 kilometer area, at least there should be have some one receiver. So like the dense network should be there. So then only we will be able to do the good or precise weather analysis. Vertically integrated quantities lateral gradient of the PWB is also possible. Continuous measurement at a network of stations, thus giving a time series data. So it's continuously, because only power required, so power is given by the solar panels, and continuously measurements we can get it. Sparse PWB information over oceans. So that means wherever only land are there, then only you will land will be there, then only you will fix the this receiver. So in this is the ocean side, it will be difficult to get this continuous, but wherever the land is there we can fix it, and we can have a continuous measurements. On the other side also, this GPS meteorology on using the space-based technique. Now here we are, what we are doing, this is a satellite where we are fixing a one receiver, and it will be orbiting around the earth, and will have a continuous observation. So it's a continuous observation, but thing is that satellite is not fixed at one place, it is continuously moving, so it will have a global coverage. So it yields a vertical profile of temperature, pressure, and water vapor, partial pressure by radio occultation phenomena. Okay, so global coverage, it enables a study of the global distribution of the temperature and the humidity over a time period, and it's a continuous measurement at a location not possible. Like first case it was continuously possible, but in second case it is a continuously not possible. But in first case we can get only the point data, at one point data, but here we can get the global coverage. So continuous measurement at a location not possible, and vertical structure of the atmosphere, temperature, and the humidity we can get it even over the global oceans. But here in first case, ocean some restriction was there because of non-availability of the this ground-based static stations. But in second case, we can get the over ocean also. Okay, but here continuously at a one place, it's not possible. So here the left side, the ground-based receiver, we are calling as a CORS, continuously operating reference stations. And we have an international GNSS service, which are having a receivers over worldwide, and if they are providing the data also freely, it is freely available, and these type of stations they established all over the world. They are also giving the data like 1 second or 30 second, whatever it is there, depending on the stations are available. Okay. So one of the application is the like troposphere. We as I told you, there is a hydrostatic delay and the wet delay. So wet delay is because of this PWV, water vapor. So precipitable water vapor estimation will do using the GNSS. So principle of ground GPS GNSS based meteorology is we will try to find out the errors in the GNSS signals, and what are the error sources. We will remove all, and we will do the modeling for the basically zenith tropospheric delay. So we will finally end up with the zenith tropospheric delay, and then we will estimate the using this precipitable water vapor. Okay. And various applications, as I already mentioned, that's the assimilation of estimated PWV in the numerical weather prediction models. For rainfall prediction, its impact on climate change, and to study hydrological cycles more effectively. GPS, GLONASS, Global Navigation Satellite System, GNSS receivers have been used to estimate the vertically water vapor content for over 2 decades. National Oceanic and Atmospheric Administration, NOAA, has a network of around almost more than 400 stations, mostly in the North America, and it deliver operational water vapor estimates. So continuously also they are giving this water vapor. Already there are some of the agencies which are having a network of stations and providing the data continuously. And UMAC's NAT GPS water vapor program, EGVAP, is there. It's from the European Meteorological Service, having more than 3,500 sites. And it's shown that to improve the numerical weather predictions, and is used for the studying diurnal variation also of the water vapor. So it's very important parameters for the basically atmospheric studies or analysis. And its advantage is there. GNSS drive PWB, it is there. It's unaffected by the cloudy conditions. So because signals are coming continuously to the receivers, so it is not like a optical sensor when we are having a cloudy conditions. It may not having a good accuracy. So, but here it is always will be we are getting the information because signals coming continuously from the satellite to the receiver. And high temporal sampling, we can get like a 1 second interval data, we can have a 30-second interval data, whatever way we want, we can fix it. Accuracy as good as or better than infrared microwave satellite sensors. Studies suggest like a less than 6% error it is there. But there are some as well the disadvantage or some points are there which need to be addressed here. So one is like a point measurement. So you are fixing a one receiver, and then you can get the information surrounding that receiver only. But if you need some area and big area information, or maybe in a state or particular area bounded by some latitude and longitude, you need to fix more and more number receivers. So then only you can get the good coverage. And it's maintenance and data collection. These are the some points are there. Maintenance, not that much still, but still we need to take care of by this like powers and regular maintenance are required. It is there. Okay, and like in satellites, when over ground, whenever it is a dumping station, there the data will be downloaded. But in here, we need to either through connect through servers or internet, and or we need to go to personally to collect the data from these receivers. So some of the places only there is only possibility we can go there, and then only we can collect the data. So this is these are the basically only the two things which need to be taken care for the effective use of this GNSS derived PWB. So the measurements collected by the GPS receiver, one is basically like a pseudo ranges. So ranges is like you can understand, like when timing at time t, then signal is maybe what we can say, that's transmitted by the satellite, and the t1 at the time t1 it is received by a receiver. So t minus t1 multiplied by the velocity of light is basically you can get the ranges. Similarly, we have a carrier phases, and then we have a usually the processing is done using the network of receivers rather than single receiver. So we are using a network of station while processing, and satellite ephemeris information also we are knowing this can be services are there to provide this satellite precise orbit they are providing, and this may be available after precise orbit of the satellites, maybe after 15 days or 2 weeks or 20 days, maybe after certain time only it will be available. But on the other side, the other parameters like maybe a rapid orbit or ultra rapid orbit, this will be available. Maybe not much time it will take. It's maybe after some time only it will be available. So we know that's a observed range, whatever we have observed, basically like t time it is transmitted the signal and t1 time it is received. So t minus t1 is basically time and multiplied the velocity of light. So this is a basically observed range, but this is having a it's a combination of the true range, because true range will be different, because the satellite will the signal will come from through the ionosphere and the troposphere, but because of that one delay will be arising. So but if you see that's a delay has to be accounted, it needs to be when we are estimating the exact range. So it's a combination of which is just like a straight line, what we can say. So observed range equals to true range plus ionospheric delay plus tropospheric delay plus ephemeris error plus relative clock biases plus noises. All these things are combination. Apart from that, if we want a good accuracy, we need to consider the hardware biases, cyclic slip detection, multipath detection. All these corrections need to be taken care for the basically precise things. Ionospheric error are mostly cancelled out using the dual frequency differences. To the first order, ionospheric delay is inversely proportional to the f square, and code carrier combinations also used to eliminate the residual ionospheric errors. Satellite clock errors eliminated using the differences of the measurement between the two receivers. So we need two receivers to determine eliminate the satellite clock errors. Similarly, receiver clock error side also can be eliminated using the differences between the two satellites. So using these and other corrections, slant tropospheric delay can be estimated. So when we are considering all these errors, so you can see here, if we remove these other errors, whatever it is there, okay. So for true range, what you need? True range, you need precise parameter of the satellite, and you know the receiver position. You can just find out the distance from the using the 2-point formula, like square root of x1 minus x2 square, y1 minus y2 square plus z1 minus z2 square. Okay, so you know the precise point of the precise location of the GPS satellite, and you know the this location of the receiver. So using this 2-point distance formula, simply you can find out the geometric distance. Now, the other observed range, this will be using the time, like t time it was transmitted and t1 time it was observed at the receiver end. So t minus t1 that multiplied by the velocity of light. And other receiver error, ionospheric error, tropospheric error, and ephemeris error can be accounted here, and then we can find out the slant tropospheric delay. Slant means at the different elevation angle, the tropospheric delay will be different. Okay, and this further can be estimated, further can be transmit. This length can be converted into the zenith tropospheric delay. Okay, so that is called the basically zenith tropospheric delay. So we know that GPS positions we are taking from the IGS in the SP3 format, as I told you. We are doing the GPS data processing, the same whatever we have told you. That's a true error. Sorry, that range formula just now, observed range, true range, or ionospheric delay. All these things we will find out, and we will fix it here, and we will find out the tropospheric delay. And from tropospheric delay, we are finding the slant tropospheric, zenith tropospheric delay. Okay, so from there we are getting the zenith tropospheric delay after doing all the processing. From this zenith tropospheric delay, zenith wet delay we are finding, and this zenith wet delay can be obtained by subtracting the zenith hydrostatic delay. So total delay is ZTD, this is zenith tropospheric delay. You can see here, it has come from the GNSS data processing, and this ZTD. From this ZTD, we are subtracting the ZHD, that is the zenith hydrostatic delay. Then we obtain the zenith wet delay, and this zenith hydrostatic delay can be estimated by the external ZHD models. And inside that, you need some pressure information, and this may be can be taken from the nearest AWS or with sensor data, MET sensor data. From the MET sensor it can be taken, or you may utilize the reanalysis data. So if there are the various reanalysis data or the model data, what we can say, this can be used to derive the ZHD models. So when we subtract the ZHD from ZTD, we get the ZWD, which is nothing but the zenith wet delay. This zenith wet delay, since wet delay is because of the water vapor in the atmosphere, this wet delay is further converted to the PWB using by multiplying a constant which is depending on the basically weighted mean temperature. So based on that, we can estimate the PWB. And further, this can be basically validated using the various available other sources like satellite data, or maybe the ground measurement or in situ measurements. Okay, so GPS data, whatever we are getting from the satellite, is in the form of RINEX. You can see here, and which we are taking from the IGS, and it contains the basically observation, navigation, and the meteorological information. And it's basically main GPS data file is an observation file, like 1 second, 30 second, the sampling rate will be there, and the data will be there. And we have a .sp3, that is nothing but the post-process satellite orbits. So it's maybe as a precise orbit we can get it, the satellite information from this. And apart from that, lot of other things are required for the basically precise estimation or accurate estimation. So like one is a .snx, it is basically contains the state location coordinates and the velocities, earth orientation parameters, antenna file. It's related to the antenna, because now antenna related file also required because different companies are making different antenna. They are having a different specification, so we need to consider this also. And we can get directly also this ZTD information from the GNSS sites. Okay, and observation file, SP3 file, SINIX file, antenna file, all these will come under this input will go to the data processing, which is further used for the basically to derive the zenith tropospheric delay, which is further derived to used to derive the zenith wet delay, and which further will be converted to the PWB estimation. Okay, so these are the basically some results. You can see here we are having a one station in the Dehradun, and we have fixed one CORS receiver here, and you can see here there are another two stations which are IGS station at Hyderabad and IISc it's Bangalore. So we have estimated the zenith tropospheric delay for both the station Hyderabad and the IISc. So you can see here, it's basically whatever IGS is giving, the services they are giving. First, we have validated using that how much difference we are getting. So it's almost closely matching with the IGS derived ZTDs. You can see for both the station Hyderabad and the Bangalore IISc. So for all for 2019, these data are derived. These data are estimated, and you can see very less difference between the at both the places. This ZTD is further used to derive the ZWD. So ZWD we have is the basically ZTD minus ZHD. So for ZHD, basically we already, as I told you, we can take the different sources to derive the basically ZSD. Like we can have a reanalysis data, we can have a met sensor data, so we already derived from the different sources. Model data we have already used. So like GPT, we have a NSAP. So we can see here from all the sources, we have taken the different sources, and then all the sources are almost matching. This a minor difference is observed between the both the sources. If you see from the different sources for this pressure parameters, whatever we have taken to derive the ZSD. Now finally, this ZWD is converted using the weighted mean temperature profile to the PWB. So if you see, that's a PWB is higher, or you can see the wet delay is also higher in the basically on year or the day number. The down you see the x-axis, they are the day numbers. So it's a 152 to 300 around. So around June, July, August, these are the basically monsoon months in the India. So the wet delay is almost high. At peak is basically around these months only. Okay, and similarly, if you see on the right side, the PWB, because of this only the wet delay is high. So the precipitable water vapor, if you see, then it is also going high. So it's around 60 mm it is going basically. Okay, and if you see the differences, it is very close to zero. It's almost maybe 1 mm or 2 mm difference. It is there 1 2 mm. So these are the analysis which were taken for the Hyderabad and the IISc stations, IGS station. Now similar, once we have proved this, developed this complete mechanism, we have also developed for our newly established station at Dehradun. So we can see here the estimated ZTD, whatever we have estimated, and whatever the ZSD and the WD, hydrostatic delay and the wet delay. So all things we have derived using this, using the GPS observations. And right side, if we can see, the PWB is around 60. It's basically, and when we compare from the other sources like a MERA model, we have compared on the down, and other GPT, PWB, and SIP PWB we have seen here. So there is almost around 1 to 2 mm difference. It is there. So you can we can see here in the down V in this table, the Hyderabad and IISc almost 1 to 2 mm difference we can observe here. Okay, so that way we can derive this PWB, and this PWB can be used further for in the weather prediction analysis. So if this is only from the using the one station, so we can have a number of stations. There's then these inputs can go to the weather prediction analysis, and which for the what we can say is basically for the basically precise predictions or more accurate predictions. Okay, so this is another analysis which we can see here in that different like as was discussing, that's whether this data should for the ZSD estimation, like data should be there either from the MET sensor or the various reanalysis data set. So these are the basically different reanalysis, because in case of non-availability of MET sensor near to the receiver, different reanalysis data can be used. So these reanalysis data analysis, because more accurate which data it is there, that we need. So different sources are there, like we have a Japanese ray analysis data, ECMWF, NSAP, MERA. So these are basically used, and for the different years 18, 19 and 20, these analyses were performed. And almost though they are having a almost similar type of observations, maybe very less, the finally it is coming 1 to 2 mm only, the differences between the all of them. But thing is that like JRA, this CCMW, MERA, JRA, NSAP are very much close. So these are the basically we can see here from the AWS, or these are basically the analysis data sets are compared with the AWS data also. So nearby AWS data we have taken, and from that also we have derived a PWB, and we have seen that how the relation from this reanalysis data to the AWS PWB, what relation it is holding. So it's holding a very good relation derived from the AWS PWB. So whatever the reanalysis or the model data results are there, very much close to the AWS PWBs. Okay, these results also published recently in another journal. And these are basically also there are some results which like for the accurate estimation of PWB for determination of rainfall detection and the monitoring. So these some references I have taken, and if we can see here, the blue scale is the basically precipitation, and the red one is the basically PWB. So wherever that spikes, you can see before that some rise is there in the PWB. So we have seen here actually once the rainfall about to there, then definitely there will be some rise in the PWB before few hours. So these analysis, this also can be used for the basically rainfall detection and the monitoring. So another example is this was all using the basically the ground-based methodology, or means the ground-based measurements. Now, if we put the satellite onto the space, or satellite onto the receiver onto the satellite, okay, and so it will continuously moving around with the satellite. So that means first we know that's basically occultation means what. So occultation is like a physical appearance of the object in the background by an object in the foreground. So during the passage of one of them against the another. So passage of the one of them against another. So what is the basically occultation is like bigger body, one body will come and it will hide the another body back in the background. So this phenomena generally we are seeing eclipses and other bodies when the like moon is coming or any other planet it is coming in between the stars. So this we already know. So when we put a receiver onto the satellite, if you see the right side, the GPS satellite, right side is GPS satellite, and put a receiver on the low Earth orbit satellite, it will start moving this side, and maybe the GPS side is going this side. So because of that atmosphere here, the signal will bend, and the receiver on the on the LEO satellite may be hiding from directly. It may be not receiving the signal through the GPS, but definitely it is coming onto the downside, and it will be basically the reflection will be there through the atmosphere, and then it is receiving the signal. So it is one side, it may be the hiding, it's not directly receiving. So radio occultation, it's basically stands for the occultation of the radio signals. Like occultation was there earlier slide as I shown you, and the radio occultation, it stands for the occultation of the radio signal, which is by transmitting by the intervening astronomical bodies having essentially an atmosphere with the signal received through refractive bending. So it is basically because of this refraction only it is receiving. Okay, so this is another kind of occultation, and we are like a space-based observation. We are calling as a for atmospheric studies for this radio occultation techniques, using the radio occultation technique. Okay, so another is a basically we are calling as a limb sounding technique. Limb sounding means you can see here this is a basically surface, horizontal lines are there, looks like. So it's a basically layer by layer information we are extracting from this. But generally it is what is happening, satellite is moving and it is pointing towards the nadir. So that is a nadir based means it's seeing the surface, basically its camera will see the surface. So this is a limb sounding, that is a nadir based sounding. Okay, so this involves the radio transmitter and different trajectories, customized receiver, and the physics of the signals. So here we are putting a one, we can see here, see we have put the receiver on the satellite, and you can see here because of the ionosphere or atmosphere, the signal is basically bending now. Okay, and wherever it is bending, like here it is bending from this point, we are defining a one tangent. Okay, and at this point we are finding a one bending angle. Okay, so from this the yellow line, wherever this nearest point, we are defining a tangent point, or we are calling as an impact point. And this point we are finding a one angle, that is a basically bending angle. So it may be when it is coming down, or it may be coming up, means rising or setting of low Earth orbit satellite with respect to the GPS is called a GPS radio occultation. A ray passing through the atmosphere is refracted due to the vertical gradient of refractivity, and during an occultation, the ray path slices through the atmosphere, and it gives the basically raw measurements. What will happen? We will get the change of delay of the signal path between GPS and the low Earth during the occultation. So this technique is having a basically used. So why it is useful? There are certain reasons are there. We are having a high accuracy. We are having a high vertical resolution, and it will work in the all weather. GPS, like earlier also, as I told you in static case, that is also working in all weather condition. And it depends on the it's basically independent of height and pressure, and it independent of radiosonic or calibration, and it is an inexpensive, means only you have to put the receiver, no instrument defect is there, and it can profile the ionosphere, stratosphere, and the troposphere. So this already I told you, there are the GPS 24 GPS satellites are there. For the positioning purpose, minimum 4 satellites should be visible. But apart from that, as I told you, that a GPS signal is required. GPS signal, that the low Earth orbit will take the signals from the GPS satellite, will receive the signals from the GPS satellite. So there are so many constellations. Apart from that, there are the GPS, there is a GLONASS, there is a Galileo. So almost around 90 sources are there already in space. And if we put a receiver of the GLONASS, we put the receiver of GPS, we put the receiver of Galileo, only receiver has to be put there. So we can get the signals from the different satellites. So receiver side, we can get the, we should have this POD antenna for the precise navigation purpose. Occultation antenna, we should have a receiver unit. And what we get the signal phase delay and signal amplitude. So nothing but the signal to noise ratio. So what we are doing here, we are just the total path delay we are finding, LIJK. IJ is basically representing the satellite to the GPS satellite to the receiver I. Okay, so receiver is J, and satellite transmitter, GPS satellite transmitter is I. So IJK. Okay, so EJ, and then it is a combination of rho IJ and Y IJ, the gamma Y IJ, we can write it, plus CI plus CJ. So rho IJ is what? That's basically geometric length. That's like a previous slide where we discussed, the same thing is here, vacuum path length between the transmitter and the low Earth orbit receiver, rho IJ. And CI plus CJ is basically measure, that's a basically time dependent transmitter, and the receiver clock errors. Okay, and nu is basically last term, it is a basically thermal noise or the local multipath or extra whatever it is there, that errors are there. So in that we can find out this Yijk, that's a basically extra delay due to the neutral atmosphere and the ionosphere. This is a combination of extra delay due to the neutral atmosphere plus extra delay due to the ionosphere. So due to the neutral atmosphere, this is a eta Ijk plus d TEC divided by the F square K. So this is the ionosphere, this because of troposphere, neutral atmosphere. So what we do here, we generally raw measurements we take from the phase from the two signals L1 and L2, and we do the clock corrections, orbit determination, and the geometric delay we find out, and from that we find out the bending angles. As I was showing in the picture, that's the ray will be bending. So bending, because and the signal will be bending angles we can find out for both L1 and L2 signal, and from that we do the ionospheric corrections and we find out the neutral bending angle. That's a one only bending angles, and from that using the Abel's transform we find out the basically refractivity N, and refractivity N, from that we can find out the atmospheric products like a T, water vapor, and the pressure. So this is the basically from raw measurement phase of two signals to these parameters can be derived. So correction of clocks, errors, and relativistic effects on the phase measurements. First we are doing compute the Doppler shift, then remove the expected Doppler shift from a straight line signal path to get the atmospheric contribution. And the atmospheric Doppler shift is related to the known position and the velocity of the transmitter and the receiver. So first compute the bending angles alpha 1 and alpha 2. From there we can get the common bending angle alpha 1, alpha A, and for neutral atmospheric retrieval bending is basically up to 50 to 60 kilometer we are taking, and for ionospheric this retrievals bending angle will be beyond the 60 degree. Okay, and this is basically an Abel's transform. Using that you can say alpha is a basically bending angle. Okay, we can find out the index of the refraction, that is N. N basically is a function of R. So basically radius we can understand. So it's basically a function of N is basically function of the bending angle. Okay, so using this bending angle alpha A we can derive this N, and that's basically index of the refraction. And from this N, that's the index of the refraction, it can be converted into the refractivity. We can find out the refractivity. So index of refraction is N and refractivity is the capital. The very small relation it is there. And this N, that's an atmospheric refractivity. It is having a relation with respect to the pressure and temperature. So P is a pressure, T is a temperature, PW is a water vapor pressure, and T is another, NE is the basically electron density. So this refractivity is basically can be it's basically depending on the pressure and temperature. So we know the N because we already have derived using the bending angle information. Bending angle how we are getting from the phase we are getting. So like that we can get it, and then we can find out this N, and N will depend on the PT. So when we know the value of N, we can derive the values of P and T. So we have our Indian satellite Meghatropic, and which is having a 20-degree inclination. So that means it works within the plus minus. It's over the tropics only. The name suggests Megha means the cloud, and the tropics means over this region only. So it's basically plus minus 20 degree it will work. Then another satellite is there for the global coverage. It is having a cosmic. So basically 6 receivers are there, and around 72-degree inclination it is there, and they are orbiting in the 6 orbital planes. So we can get this. You can see the global coverage is there. Here we are getting the only the over the plus minus 20. So depending on the missions, so whatever as per our requirement, we wanted this region only, so we have developed such orbit. And if the global coverage, so we need to develop such an orbit basically. Okay, so this is basically a comparison GPS, GLONASS and the Galileo. We can see here there are the 24 satellite in GLONASS, GPS 24, Galileo we have a 30. So 3 orbital planes are there, and GPS we have a 6 orbital plane, Galileo we have a 3. So orbit is around 55 for GPS, but GLONASS we have a 64.8 something, and then Galileo is around 56 degree. Orbital altitude is it's basically 20,180 kilometer. So like these are the basically orbital comparison it is there. And finally we have done this analysis, and that we can see here we have collected the points, the impact points which are over the basically Indian region, whole Indian regions. So these are the total impact points. Out of that, we have collected only the those points which are basically from surface to 1 kilometer range minimum are there. Okay, and considering these points, we have basically fixed one column over that region around that point, and we have created the grid around 2 degree by 2 degree. Okay, and then we have seen in that particular column of 2 degree by 2 degree how many points are coming. And finally, using that, we have developed a vertical profile of this water vapor. So we can see here the red one is basically derived using the cosmic data, whatever the global coverage data satellite having, and we compare with the other sources. It is almost very closely matching, and very within 1 degree only, 1 millimeter that difference is observed. Okay, and that too, and we can see here up to 600 HPA or that many only the water vapor is higher, and after that there is no water vapor. Okay, so maximum water vapor will be lying within the maybe the 15 or 20 kilometer only. That's after that no water vapor will be there. Okay, so in the lower troposphere only the more water vapor will be there. So we can derive this using this data. We have derived it, and we have developed this, or we have estimated this the vertical profile of this water vapor. Okay, we can see the right, that's a difference are very close to zero only. Okay, in all the profiles. So this is also like ground-based technique. This is a space-based technique is also very promising, an atmospheric observing system for both weather and climate. It's having a high vertical resolution. It's having a high accuracy. It's work in all weather, and no instrument drift it is there. And it will be valuable to climate change analysis, validating of climate simulations, operational weather predictions, ionospheric research, and space weather forecasting. And so is useful for calibrating other observing system as well. Okay, so definitely a lot of missions are there, a lot of satellites data are available, so we are working on that. So this was the basically these are the references which generally from that some of the references I have maybe I have used, and for this presentation purpose. Okay, so